Assalamu alaikum and good morning. So today we're going to look at some questions from topic 8, exercise 8.1, and after this we will be looking at topic 7, exercise 7.1. So for this exercise 8.1, which is on reaction kinetics, I have asked you to vote the questions that you want me to give further explanation on. The most highly voted question was actually question 17, but I've got a number of votes for the other questions as well. So I'm just going to go through that really quickly. The first question we're going to look at is question 1. Which of the following factors can affect the value of the activation energy of a reaction? Okay, so for this one, you have to remember that only catalyst has the ability to lower down activation energy. Other factors like adding concentration, increasing concentration, increasing pressure, increasing temperature, or surface area will have nothing to do with changing the value of the activation energy. What they do is either increasing the collision between the molecules or increasing the number of molecules that have energy enough to overcome the activation energy. But the value of activation energy for a particular reaction cannot and will not be changed unless by the addition of catalysts. Okay, so I hope that explains question 1. Next, question 3. So we've got a Haber process here, and it is in a dynamic equilibrium. Its enthalpy change is a negative number, so that means forward is exo and reverse is endo. If you're wondering why I put my exo on top, is because the arrow on top is going in the forward direction and the arrow at the bottom is going in the reverse direction. What happens to the rate? So I think a lot of you are looking at the shifting or the position of dynamic equilibrium here. But when we talk about the rate of reaction, regardless if it's a regardless if it's an exothermic or endothermic reaction, the increase in temperature will result in an increase in the proportion of molecules having energy equals to or higher than the activation energy. So that means regardless of endothermic or exothermic reaction, increasing the temperature will increase the rate of reaction. It's a different story if the question is asking about the yield or the position of the equilibrium. When you increase the temperature, the position or the yield of equilibrium will be affected in such a way. Increasing temperature will favor endothermic reaction. That means the dynamic equilibrium will be shifted to the left and you will have more reactants than products. However, the question is not asking about the position or the yield, it is asking about the rate. So this is actually a good trick question. This part is the trick, okay, into thinking that the increase in temperature is only favoring endothermic, but it's actually also, the increase in temperature is only increasing the rate of reaction of endothermic, but actually it increases the rate of both endo and exo. So the answer is B for question 3. Next question is question 7. Okay, so in order to do this question, you need to understand the reaction pathway. First, if we are looking at going from Z and Y as your reactants, okay, that's your reaction pathway. You started at a certain energy here, and then you overcome the activation energy. So that's your activation energy. Once your molecules have overcome this activation energy, they will react and turn into products. That is the forward reaction. Okay. And I know the arrow is only showing a single arrow. If we're looking at the reverse reaction, we have to start from the products, W plus X. In this case, if I'm looking at the reverse reaction, W and X is now my reactants. So I've only just reversed them, okay? And then, so this is the activation energy of my reverse reaction, that hill that I need to climb. And then once I have overcome, or once I have reached my highest peak, okay, then of course I can turn into the products. That means reaction will for sure happen. Okay. Now another thing to look out for my forward reaction, which I start from Y plus Z to W plus X, the energy of my reactants is higher than the energy of my products. That means it is an exothermic reaction. Okay, if I'm looking at the reverse, starting from W plus X, going to Y plus Z, the energy of my W plus X, in this case, it becomes the reactant because I'm talking about the reverse reaction, okay? The energy of my W plus X is lower than the energy of the product. How do I know? I just look at the level, because on my Y-axis, it's energy. Okay, so energy of reactants lower than energy of products. That means it's an endothermic reaction. You remember how we draw the reaction pathway of an endothermic reaction? It looks like this. So that's the same thing here. The reactants is lower in energy than the products. Okay, which statement is true about the reverse reaction? See, they want us to talk about the reverse reaction, okay? Right, so the answer is D, activation energy. Okay, I need to color code this. So forward reaction, I will use green. Okay, forward reaction, I'm starting from Y plus Z here, and then I'm going up. So that means that is my activation energy for forward in green. If I am going in reverse, which now I'm going to use my blue, I start from W plus X. Start here. For forward reaction. Sorry, start here for reverse reaction. At this point, you should already know how to identify your activation energy from your graph, enthalpy change from your graph of reaction pathway. Okay, so if I'm starting from W plus X, that means there is a minimum energy I need to overcome in order for reactions to happen. So my reverse reaction, the activation energy is this much. So you can see the green and the blue arrow. The blue arrow is bigger. Okay, so that means the activation energy of the reverse reaction will be bigger, and it has a positive delta H because, as I said, it's an endothermic reaction. Right? I'll just label this Y plus Z, start here for forward reaction. Okay. Next question is question 8. A student measured the rate of reaction at 2 different temperatures. They observed that the rate of reaction roughly doubled. Okay, so this one is more to remember that I emphasize when increasing temperature that there are 2 points. The first point and the most important point is the proportion of molecules having energy equals to or bigger than activation energy increases. And then the second point, which is the less important point, is the kinetic energy increases. And most of you are so built on with this idea that the increasing temperature will increase kinetic energy. Yes, that was true, and that is still true, but that is only a small factor. The bigger factor is always, when it comes to temperature, always the number of molecules having more than a certain amount energy. That means the number of molecules having energy bigger than activation energy is the main factor that affects or explains the increase in temperature. Okay, so I would not be surprised if a lot of common mistakes would be B. Okay, a lot of common wrong answer to be B, but it's not D, because increasing in collision is only done by increasing in concentration and pressure. So you need to understand changing different factor will have different explanation on how they increase the rate. For example, catalysts, they increase the rate by providing a lower activation energy. Okay, temperature, they increase the rate by increasing the number of molecules having energy bigger than activation energy. Next, concentration and pressure, they work the same way. Okay, so only concentration and pressure have the same explanation. If you increase the concentration or pressure of your reactants, the number of effective collisions will increases, because now the molecules have less space. They are close to each other and they are more likely to collide. So you can see that these three are different explanations, yet all of them have the same effect on the rate of reaction, which is to increase the rate of reaction. So you can't just simply say, oh, increase in temperature, the effective collisions increases. Yes, but that's not the explanation. Okay. Next is question 12. The dotted line curve on each graph below represents the corresponding distribution for a gas at 300 Kelvin. Which solid line? So dotted line is low temperature. Okay, so we look at graph D. Dotted line is low, and then the solid line is high temperature. So this is the criteria. Okay, so there is actually something wrong with the graph. They shouldn't touch 0, but if you can see that they, well, yeah, they shouldn't. Okay, like this. This is a good graph, but it's the wrong. The peak is wrong. Okay, so what happens when I have? Maybe I'll change the color low. So this is my Maxwell-Boltzmann distribution curve at low temperature, okay, in orange. And then I increase the temperature, right? So if you imagine when increasing the temperature, my number of molecules having energy higher than the activation energy would be high. So I would imagine my graph to shift to the right, because the right is the direction of increasing molecular energy. So now my molecules have higher, generally higher energy shifted to the right. Okay, so if you look at your notes, increasing temperature will, one, shift the graph to the left. Secondly, the peak, Okay, the peak is the highest part of my graph or my mountain. Okay, the peak will be lowered down, and lastly, the tail will be a little bit higher up. So you have to refer to your notes for this. Okay, so now it's shifted like that, but the peak is much lower and something like that. Okay, so if you look at all these options, option D is the most accurate. A, don't get confused. Your dotted line is the low temperature. Your solid line is the high temperature. So A is wrong. B is correct because the shifting is correct, but the peak is of the same height. That cannot be happened. When you pull your graph and at the same time you want to keep the area under the graph the same because the area under the graph represents the number of molecules, the peak has to be lowered down because you're pulling it, you're stretching it, okay? This one is definitely wrong because you have higher peak. That means the number of molecules will increase. You can already see from the graph alone, the area of the graph for the solid line, which is at higher temperature, is bigger than the area under the graph for the dotted line. All right, so that's why the answer is D. Lastly, question 17 is I would have to say it's quite a challenging question, okay? So I've only given you one factor, but there's also another factor, right? The equation for this reaction is when you decompose hydrogen peroxide in the presence of a catalyst, it will be it will produce water and oxygen, okay? So curve 1 was produced from measuring the decomposition of 100 centimeter cube of 1.0 mole per dm cube of hydrogen peroxide. Okay, which alteration to the original experiment conditions would produce curve 2? My first hint is that, look, your y-axis is the volume of oxygen produced. So you have increase in products. You see, graph number 2 ends up producing bigger volume of oxygen than experiment 1. What is the main factor that cause your volume or your amount of product to be increased? Only by increasing concentration of your reactants. Okay, if I add more hydrogen peroxide, of course I will get more oxygen. So that was my main hint. I wasn't thinking about anything else. All right. So reaction 2 suggests that more oxygen is formed. And this is caused by increasing reactant. And your only reactant here is H2O2. Increasing catalyst will not do anything to increase the volume, will not do anything to increase the yield. Okay, it will only speed up the reaction, the rate, but not the amount of your products. Okay, now another thing that you must notice is the gradient. Okay, so if you look at reaction 1, I'll use green for that. The gradient, which is the rate of, I'll just write down rate 1, okay? And then you compare to the rate of reaction 2. Reaction 2 has a lower or a slower rate. Now you may ask, why is it that I'm increasing the amount of hydrogen peroxide, yet my reaction is getting slower? The reason is because of the concentration. Initially, you've got 1 mole per dm cube of hydrogen peroxide. You are adding 0.1 mole per dm cube of hydrogen peroxide. Overall, you are increasing the concentration, you are increasing the amount, okay, number of moles, but the concentration is diluted. Okay, it's not the same concentration you're adding now. So that's why the rate of reaction slows down. So the second explanation is a little bit not that straightforward to understand, but I think my first explanation is that's the only way to explain how you can get more products formed. Increasing the temperature, you will not get more products formed. You will only get the products to be formed faster. Adding more manganese oxide, same thing, faster. Adding water. Now, if you add water, what happens is that water is your product, okay? And you will also dilute your H2O2, right? There's no effect on the amount or volume of oxygen produced. So the only possible explanation is D. When you add reactants, the amount of products will also increases, even though the reactant has a much lower concentration. There is still some number of moles in that 1 dm cube. Okay. All right, so that is all for exercise 8.1. Now I would like to move on to exercise 7.1. First, to look at question 7C. So I'm just going to choose some questions so that you are able to complete this exercise on your own. Okay, I will provide the marking scheme and then you use this as a revision. Just because I'm not doing it with you together or I don't assign you to do the questions, it doesn't mean that you don't have to do it, or it doesn't mean that it's less important. Okay, now looking at question 7, we've got a dynamic equilibrium system of hydrogen iodide dissociating into hydrogen and iodine. Okay, notice that your hydrogen iodide is in gas state, hydrogen is in gas state, and iodine is also in gas state. Okay, I would just like to go to part C. Suggest and explain why it would be more difficult to determine Kc for this equilibrium at room temperature. Hint. Something will change the state at room temperature, and that something is iodine. Okay, iodine is a solid at room temperature. And what do we know about the Kc of solid? What do we know about the concentration of solid? It cannot be measured. Okay, so that would be a problem. That's a problem why sometimes things can't just happen at room temperature. Okay, let's see. So at room temperature, iodine is a solid. 1 mark. How many marks? 2 marks. So the concentration of iodine gas, iodine solid, oh, so that's 1 mark, will not be included in Kc expression. Okay, so this 2 points will be 1 mark. Okay. What's another point? Suggest why it will be more difficult to determine Kc for this equilibrium at room temperature. Okay, so if the temperature is low, There's also another reason for it. Reaction is slow, or we say it takes longer to reach equilibrium. Okay, so that's the second mark. So you do not want a reaction to happen at room temperature if normally it happens at, at a very high temperature, because yes, changing temperature will also affect the rate of the reaction, or the rate at which your system achieve equilibrium. Sorry. Okay, next is question 10. Question 10 is here. All right. So question 10 is a reaction between methanol in the presence of a catalyst, hydrogen ions, to form acetal A plus H2O. Okay. So here they've got reactants. I'll just label them. Catalysts and products. Okay. We are given the initial moles. Is this moles? Concentration. Okay, you're given the concentration already. So initial concentration, initially you started with some amount of reactants and zero amount of products. So you don't have products to start with. However, at equilibrium, you have produced some amount of product. Okay, so that means if I were to have another row, additional row that I usually have at reacted, so and produce. Okay, this two row is actually just the same at equilibrium. Okay, it's just that one is in terms of X and the other one they want you to find in terms of number. So the missing row here is the reacted / produced row, which is the most crucial because that's the one that you can use mole ratio. Okay, so if you started with 0 and at equilibrium you have 0.025, that means you must have produced 0.025. All right, so I will just use X. That means you have produced X amount. Remember, this is my, maybe I should draw a line so as to not confuse you. I don't have space, that's why I'm doing it like this. So please take note that that is additional middle row for reacted / produced. Okay, so I'm going to use in terms of X first, because this column here wants you to answer in terms of X. Okay, once I know one information in the middle row, I can just use my mole ratio, and nicely enough, all my mole ratio are 1, excluding the catalyst. Okay, I'll talk about the catalyst later on. So if I have produced 1 mole of acetal A, if I have produced X mole of acetal A, I would have produced X mole of H2O as well. And then if I have produced 1 mole of acetal A, because the ratio is 1 mole, if I have produced X mole of acetal A, X mole of methanol would have reacted, and X mole of ethanol would have reacted as well, because they are all 1 to 1. So nicely, the concentration of your reactants reacted would be X as well. So I'm just going to change my X because it looks like cross. Okay, then I can work out my equilibrium concentration expressions in terms of X. Okay, let's start with the products first. Remember, to get the products at equilibrium, its initial plus produced is equals to E. If I want to find reactants at equilibrium, I have to take initial minus reacted equals to E. So there is a difference there. Okay, so if my acetal, since I already know all the three, well, sort of all the three values of acetal, so that means at equilibrium, initial 0, 0 plus X is equals to E. So that means at equilibrium for my product, there's X mole per dm cube of acetal A. Okay. For water, since it's a product, 0 plus X is my concentration at equilibrium. 0 plus X is just X. All right. For my reactants, methanol, CH3OH, and remember, reactants, I have to use initial minus reacted. So for my methanol, initial is 0.10 minus X. Okay, initial of methanol minus how much have reacted. As for my ethanol, since it's already given, it's 0.20 initial minus reacted. So it's 0.20 minus X. Okay, can you see that from here? Oops. From this, I'll use a different color. From this column, 0 plus X is equals to 0.025. That means X is 0.025, and you just sub in value of X for all the expressions. Okay, first example, I've got X concentration of H2O. So that means the value at equilibrium is 0.025. Now you want to find the concentration at equilibrium of methanol and ethanol when you sub in value of X, which is 0.025. Okay. As for catalyst, please take note that catalyst stays unchanged. So catalyst will still be 0.05 all the way through. That's the most crucial thing about catalyst. Okay, so it does not get changed in a reaction. Let me just, okay, so please complete this. And then I'll move on to the next question if you need to screenshot this question. The next question is question 11. Okay, sorry, once you have completed this table, and if you take the value of the very last column, because those are the concentrations at equilibrium, and these are the values that you want to use in your Kc expression, okay? You can hopefully work out the Kc values. Okay, now question 11 involves a little bit of calculation, so I will help you with that. We've got ethanoic acid reacting with alcohol, so I will just write down acid, alcohol, and also I think there is a mention of an acid catalyst. Okay, so catalyst is H plus, all right? And this is our equilibrium. Okay. In an experiment to determine Kc, a student placed together in a conical flask 0.1 mole of ethanoic acid, 0.1 mole of an alcohol, 0.005 mole of hydrogen chloride catalyst. The flask was sealed and kept at 25 degrees Celsius. Okay, so you need to understand that these values are all initial. Okay, initial values, initial number of moles at initial. So I'll just add that 0.10 for acid, 0.10 for alcohol, and for the catalyst 0.005 mole. But we all know that the catalyst will not be affected, okay? But we cannot ignore it. It's there. After this time, so after you have reached at equilibrium, so you know the number of moles at initial, right? The question is now the number of moles at equilibrium is the question. Okay, and here. So I'm guessing initially you've got 0 moles of products. Okay, the question is the number of moles at equilibrium because you would need that to calculate your Kc values. The initial will help you to work out the values at equilibrium. Okay, so it's not at all useless. You still need them. After this time, the student titrated all of the contents of the flask with 2 mole per dm cube of sodium hydroxide. So remember, after you have achieved the equilibrium, I now hate this box for being here. Shouldn't have drawn that. So after leaving this, okay, I'm just going to delete this whole thing. So 0.10, 0.10, 0 and 0. Okay, so these are the ones that we want to find. Okay, this is 0.005. Right, so after 7 days, we have some amount of acid and alcohol at equilibrium. We also have some amount of products, which is our ester and water. But the question is now we want to find out how much. Okay, so we use sodium hydroxide. Remember, sodium hydroxide would react with acid. Yeah, if you look at your system, this whole thing, remember your system is a closed system, so you cannot remove anything out, you cannot add anything else, but you can do a titration with it. Okay, so sodium hydroxide would be titrated against this system, but the problem is you've got 2 acids here that sodium hydroxide can react with. The first acid is your ethanoic acid. Yes, that's the value that we want to find because we want to know how much of ethanoic acid is left at equilibrium. That's why we do the titration. However, there is also the acid of the catalyst. So that becomes a problem. React with acids, ethanoic acid, and catalyst. The catalyst, as we know, initial is equals to at equilibrium. We know that at equilibrium, we will still have 0.005 mole of catalyst. Okay, 0.005 mole. Okay, let's do the question first as we go along. Calculate the amount in moles of sodium hydroxide used in the titration. Okay, so I know the concentration of sodium hydroxide. So number of moles of sodium hydroxide is equals to concentration times volume. So I'll leave you to that. Make sure your volume is converted into dm³. All right. So then you get some value. Now, this is the number of moles of sodium hydroxide that reacts with both ethanoic acid and catalyst. So this number of mole represents sodium hydroxide that reacts with both ethanoic acid and catalyst. Okay, so what amount in moles of the sodium hydroxide reacted with the hydrogen chloride only? So what you can do is take the number of moles of sodium hydroxide total, which is your answer from question B, part 1, minus number of moles of hydrogen chloride, which is your catalyst. Oh, okay. So the catalyst is actually HCl. I just put down H plus, which is fine. All right. So you will take okay. Sorry. Number of moles of sorry. What amount of in moles of this sodium hydroxide reacted with the hydrogen chloride catalyst? 0.005 mole of hydrogen. Okay, so this one you would need to know the mole ratio because HCl reacted with sodium hydroxide in a 1:1 ratio. Okay, no need to write down the full because we know already. So if you know the number of moles of sodium hydroxide, the number of moles of hydrogen chloride catalyst will also be the same. Okay, because of 1:1 mole ratio, right? Then oh, so they are looking at separate experiment here. One reaction is sodium hydroxide with ethanoic acid. The other reaction is sodium hydroxide with the catalyst, which is the HCl. So you have to look at them at separate reaction. Okay, right. So the balance equation I would give you is CH3CO2H plus NaOH to give you, so you don't have to work this out. I will just give it to you straight away. And again, they are in a 1:1 reaction. Okay, so hence calculate the amount in moles of sodium hydroxide. Now, the number of moles of sodium hydroxide, whatever value you get from here, is actually mana? Hence calculate the amount in moles of sodium hydroxide that reacted with the ethanoic acid. Okay, maybe it's easier for me to give you the answer because I think it's difficult now. Okay, so I'll just give you the answer. The answer for this is 0.045. Okay, and then the second part, the number of moles of sodium hydroxide that reacted with the hydrogen chloride is actually the number of moles of catalyst because you've got 0.005 mole of catalyst. So the number of moles of sodium hydroxide that reacts with it is also 0.005. So since NHCl is 0.05 mole. Hey, so ignore what I said earlier about the number of moles of sodium hydroxide from here, okay? So sodium hydroxide would be 0.005 mole as well. So that number comes from here, okay? So this is the mole that reacts with catalyst only. This is the number of mole that reacts with catalyst plus ethanoic acid, okay? Calculate the amount in moles of sodium hydroxide that reacted with the ethanoic acid only. So you take the number of moles of sodium hydroxide with, okay, so this is going to be long. Number of moles of sodium hydroxide, ethanoic acid plus HCl is 0.045. Number of moles of sodium hydroxide with HCl only is 0.005. Now, how do you find the number of moles of sodium hydroxide of ethanoic acid only? Okay, so that you have to work out. Once you know the number of moles of sodium hydroxide that reacts with ethanoic acid only, then you can actually find the number of moles of ethanoic acid. Why? Because sodium hydroxide and ethanoic acid is 1:1. So whatever your number here is of the number of moles of sodium hydroxide, it will also be the same number of moles of ethanoic acid, and this is already at equilibrium because this reaction, this titration is carried out once or after equilibrium has been reached, right? So remember, once we know the value of the equilibrium, I can find the middle row reacted and produced, and then I can work out the Kc. Okay, so the only difficult bit is this part, the calculations of sodium hydroxide that only reacts with ethanoic acid. Okay, we don't want to know, or we don't want to include the number of moles of sodium hydroxide reacting with the catalyst, which is HCl. So if you want to copy this down, please screenshot now. I will move on to the next part. Okay. So use your results from B to calculate the amount in moles of ethanoic. Okay, so this is where I was talking about. Once you get the number of moles of sodium hydroxide with ethanoic acid only, that is equals to the number of moles of ethanoic acid CH3COOH, because it is 1:1. Okay, if you get the correct number of moles from the previous calculation, then you can just sub in the numbers here, 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 and here. Okay, and to find the other information about their equilibrium values, you need to add the missing row here. Okay, they don't add the reacted and the product row, produce row. So you have to edit yourself. Okay, so that's the biggest trap for you, right? You just assume that, oh, I'm given the initial amount, I'm given the equilibrium amount, so I just take the mole ratio for the equilibrium. It's 1:1. No, it's not like that. Okay, you have to use this middle row and utilize the mole ratio. Okay, so whatever answer you get here will be the value at equilibrium. Right. Part D, esters are hydrolyzed by sodium hydroxide. So that means ester is another thing that could have reacted with sodium hydroxide during the titration. Okay, sodium hydroxide could have reacted with esters too during the titration. However, during the titration, sodium hydroxide only reacts with ethanoic acid and the hydrogen chloride, but not with ester. So what is the reason for that? Okay, so the answer is you just have to assume that the reaction with ester is slow so that it becomes small or negligible, or you can say that the activation energy of the reaction of sodium hydroxide with ester is high. Okay, so these are just some suggestions. We don't know that, but it's an acceptable suggestion. Okay. What would be the effect, if any, on the amount of ester present if all of the water were removed from the flask? Okay, so this means if you look at the system, okay, you are removing H2O. That means you are decreasing the concentration of the product. So that means your equilibrium would want to increase the concentration of products by favoring the forward reaction. So we say that equilibrium moves to the right-hand side, more ester would be produced to restore the equilibrium or to resist the change according to Le Chatelier's principle. Okay, so that's just another way of saying the concentration of product is reduced by removing the water from the system. Okay, I've got two more questions actually, which is question 14 and question 16, but I think I will just stop here for now. I will continue this in another video. Okay, question 14 and question 16, because I think I can't just skip it because that is involving KPs and you haven't had a lot of practice with KP calculation. So far, we've only looked at KCs. Okay, after this, there is a Microsoft Forms for you to fill in. Basically, they are based on the calculations that we have done in this exercise. All right. Assalamualaikum and thank you, everyone.